The last statistic that we're going to study this term is called a chi-square. I know that word looks like it should be pronounced chi because it has a CH, but it's a Greek letter. It looks like an italicized X, and it's called chi. So the chi-square is a statistic that we're going to cover only conceptually. I'm not going to teach you how to compute it. In real life, if you need to compute it at some point, you can usually use a calculator, and understanding how it's computed doesn't really help us understand conceptually what it's doing. And so unlike all of the other modules where understanding the mathematics of it can also help you understand how the statistic functions, the chi-square is sufficiently understandable just talking about it conceptually. So before we talk about chi-square, we really need to revisit a term that we learned in Module 1. Long time ago, we learned the word parameter. Remember that hypothesis tests are used in all the tests we've done so far to test hypotheses about a population parameter. Remember, this is a value, a number that's computed from the entire population. And we use the word statistic to represent the guess about what the population parameter is just based on our sample. So parameters are numbers computed from a population, and statistics are numbers that are computed from a sample. So all of the statistics that we've done so far are called parametric statistics because they're trying to estimate population parameters. So we call them parametric. Parametric tests share several assumptions. We've talked about these in brief several times before, but I just want to highlight them here now. First, they assume that you have a normal distribution in the population. Or even if you don't, they assume a normal distribution in the sampling distribution. They assume that you've got homogeneity of variance in the population. So remember that if you've drawn two samples and they vary to different degrees, like if the spread of one population is different than the spread of the other, then you have to either make certain corrections or you can't even run your statistic. So they assume that the variance in your populations are homogeneous. They're the same. And finally, they assume that there's a numerical score for each individual. And this is measured on a number line, either interval or ratio. And again, from Module 1, you remember that interval numbers are those that don't have a true 0 point, but the distance between each value on the number line is the same. And the difference between interval and ratio is that ratio numbers are the same, but they just have a true 0 point. When you have 0 on this scale, it means you have nothing of that variable, whatever that is that you're trying to measure. Non-parametric tests are needed if your research situation doesn't meet all of these three assumptions. So some examples of this might be like sometimes it's not easy or possible to obtain an interval or ratio scale measurements. A good example of this might be if we wanted to know whether the proportion of men versus women was different in certain majors. If your dependent variable was the percentage of men and women, those are not measured on the interval or ratio scale. Male and female are categories, so that's a categorical measurement. And if you were using that as your dependent variable, then you would have to use a non-parametric test because you couldn't compute the average of males and females. If you had a situation where you had high variance in the original scores, then sometimes non-parametric tests deal better with those high variance situations. An example of this would be like if, as you recall from several previous modules, where the variance was so high in two different samples that the samples overlapped a great deal, the scores were overlapping each other, then you would find that it was difficult for a parametric test to detect a difference just like your eyes can't detect the difference between scores that are intermixed with each other so much on a number line. If they're intermixed a great deal because there's so much variability, then it's difficult for not only your eyes to detect, but it's difficult for the statistics to detect. And so in a situation like that, a non-parametric test can be better. If you have non-linear relationships, those might be curvilinear or exponential or something like that, you can use a non-parametric test, and often it will simplify the nature of your relationship to cause it to be linear. When you change, for instance, from a ratio scale to an ordinal scale, it will kind of force the data to take on a linear relationship. But then you can't run traditional parametric statistics on it because it has to be an interval or ratio scale in order to run parametric statistics. So if you change it to an ordinal variable, it might improve the linearity, but it's no longer a parametric statistic. If you have undetermined scores or infinite scores that cannot be measured but could be categorized, then you might be able to use a non-parametric test. So for instance, if you have a scale that says, how much money do you earn in a year? And your options are like 0 to 10,000, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, and so on. And your top category was like greater than 150,000. That is an undetermined or infinite score, because somebody might be earning $200 million a year or $1 billion a year or something like that, and that would be an undefined or an undetermined score in this scale. It would be categorized the same as somebody who earned 150 or somebody who earned 200. Whatever somebody earns over 150 would all be lumped together. Now, you can categorize those into an ordinal scale. You could say anybody who earns 150 plus, that is indeed greater than 140. That's greater than 130. So it can be ordered and categorized, but if it's undetermined, then strictly speaking, you shouldn't run a parametric statistic. Now, in real life, we often find that these rules are a little overly strict. So sometimes people in a situation like this really would run a parametric statistic, but they would just interpret the results with caution. All right, so now with that foundation, I want to move back to the statistic called the chi-square. There are two types of chi-square. The first one is called a goodness of fit. So a chi-square is a non-parametric test. Participants are classified into nominal categories, and the statistic is run on frequencies as the dependent variable. So an example of this would be if you earned an A, a B, a C, a D, or an F in a class, you could figure out how many people got each of those scores. You recall the format for a frequency distribution graph and a frequency distribution table back from Module 1. In this case, 5 people got an A, 11 people got a B, 16 people got a C, and so on. If you had those proportions listed out here as your obtained percentages, then you could compare those percentages against some hypothesized null hypothesis. In this case, we might say it's the same amount in each category. That might be our null hypothesis. But it doesn't have to be the same amount in each category. You might compare it against a null hypothesis in which everyone got an A and nobody got anything else. But whatever you're comparing it against, the question you're asking is, do the percentages that we obtained differ from what we expect in the null hypothesis or another null hypothesis, whatever we've chosen? So if 13 and 3 and 40 and 15 and 5 was different from 2020, 2020, 20, then we would reject the null hypothesis and we would say people did not get what we hypothesized that we would get, and the goodness of fit of our obtained model against the model that we predicted is not a good. It's not a good fit. Another example of a chi-square statistic is called the test for independence. In this case, both the variables x and y are categorical. An example of this is a researcher wants to know whether there's a relationship between birth order and personality type. He or she categorizes both variables and recodes them as 0 and 1. So you can see here an example of how that might look. Birth order has two possible options. You can either be firstborn or laterborn, and that would be coded as a 0 or a 1. And your personality could be either introvert or extrovert. That's, again, 0 or 1. And if we had a bunch of people who are listed out in this table, you could give them 0s and 1s for those two variables. If somebody's birth order were firstborn, then you would give them, firstborn child is 0, then you would give them a 0 here. And if that person was an introvert, looking back at our codes, we would see that an introvert is 0, so we would award that person a 0 for their personality. If the second person were a thirdborn child, then we'd give them a 1. And if they were an extrovert, we'd give them a 1. And if you went through all of these first, secondborn, fourthborn, secondborn, extroverts and introverts, and gave them scores for each of those things, each person would end up with a 0 or a 1 for their birth order, and a 0 or a 1 for their personality. And then you could figure out how many people fall into each of these combinations. A firstborn introvert, a firstborn extrovert, a laterborn introvert, and a laterborn extrovert. And so I've taken these 0s and 1s here and put them into this table, and you can see here that what you end up with is 2 firstborn introverts, 1 laterborn introvert, 1 firstborn extrovert, and 4 laterborn extroverts. If you look at this overall pattern, you can see that there's a relationship between these two variables. The percentages that you see in one of the categories, whether they're first or later born, depend on the other category, whether they're an introvert or an extrovert. Or you might swap them around and say that the personality type depends on their birth order. So in this case, you can see that people who are later born are far more likely to be extroverted. People who are firstborn are far more likely to be introverted. Now you might notice that ANOVAs and chi-squares are set up very similarly. An ANOVA setup, what we talked about several modules ago, might look something like this. You have a score. If you're evaluating the mean scores that are earned in a stats class, for each group, you might see the average score for males who are psych majors and females who are psych majors, for males who are another major, and for females who are another major. And you can see, comparing these, that there are perhaps differences in the averages for each of these different types of groups. This right here would be called a 2x2 ANOVA, because we have 2 levels of major and 2 levels of gender. Those 2 variables of sex and major are your 2 factors in your 2x2 ANOVA. But a chi-square might be set up quite similarly, where we might evaluate the percentage of students who passed a stats class for each group, instead of computing their actual average score. So here you might have still males and females, psych majors and other majors, and you might say the percentage in the dependent variable here would be the percentage who passed in each of these groups. And you might say, oh, it looks like there might be differences among the percentage of people who passed in each of these groups. Notice that the difference between these statistics is that you're comparing means in the ANOVA, but percentages in the chi-square. Now I have to define here what I mean by percentages, because one might say that these scores right here that are obtained look an awful lot like percentages. Somebody might be getting 85% in the class, or 83%, or 89% in the class. Indeed, they could, And that would be appropriate to analyze using an ANOVA. So what do I mean by percentages here? These are percentages in a binomial variable. A binomial variable is one in which there are only two options. You can either pass or fail in the class. And these percentages are indicating the percentage of students who did that one thing that you're interested in, the percentage of students who passed. So 90% of students passed, but this is not their average score. Their average score might be something over here reflected, but the percentage who passed is indicated in this scenario. So whenever you're using a chi-square, what you're doing is you are calculating the percentage of people who did this thing, not measured on an interval ratio scale, but rather on a categorical scale. So some other examples might be if you want to see the percentage of students who are male in each group, or the percentage of students who drive a red car in each group, or the percentage of students who ate breakfast in any given group. The point here is you have an option that people could do or not do, and you're seeing what percentage of people did that thing that you could either do or not do. So I want to walk through some examples here really quick and have you decide whether you think you should use an ANOVA or a chi-square based on what we just described. The first one, Samantha wants to know if more customers coming to her store are satisfied with their experience after she installs a new childcare center. She asks people to complete a one-question survey that asks if they were satisfied with their visit. And the answers to those questions are yes or no. Were they satisfied with their visit? Yes or no. She compares the responses before and after she started the childcare center. So you need to figure out whether you should use an ANOVA or a chi-square in this situation. In order to answer this, you should figure out what is the independent variable and what is the dependent variable. And if the dependent variable is measuring averages, you'd use an ANOVA. And if it's measuring percentages, you would use a chi-square. So go ahead and pause your video, take a moment, and answer that question. Hopefully you realize that in this situation you need to use a chi-square. And the reason is because she's comparing percentages of people who said yes, they were satisfied with their visit, before versus after she started the childcare center. So that would allow us to compare on a binomial variable, something that you could either do or not do. You could either say yes or no. We're comparing the percentages of people who did that. And so hopefully that makes sense that we would use a chi-square. What about this one? You have two independent variables in your study. You want to know whether gender, male versus female, and race, black, white, Latino, or other, impact your success as a restaurant manager. You track thousands of restaurants across the nation and measure success as the net amount of profit earned by the restaurant in dollars. So, which would you use, an ANOVA or a chi-square? Remember, map out your independent variables. Perhaps use a little chart down here that shows the levels of one variable, the levels of the other variable, and then inside the cells you have to think, what is my dependent variable? And if it's an average, you'd use an ANOVA. If it's a percentage of something that you either could or couldn't do, you'd use a chi-square. Hopefully you recognize in this situation that you should use an ANOVA, and the reason why is because the dependent variable that you're measuring is the net amount of profit earned by the restaurant in dollars. This is not a percentage. You can compute the average number of dollars that restaurants are earning, and that would allow you to use an ANOVA. This specifically would be a 2x4 ANOVA, and that's a factorial ANOVA. Finally, What about this one? You have a friend who is a lawn care specialist. He wants to know whether aerating really helps grass grow more healthily. He randomly selects 25 customers and aerates their lawns for free. A month later, he goes back and checks a box for each lawn. They're either green or brown. He compares the 25 lawns he aerated to the 25 lawns to the lawns of 25 other customers whose lawns he didn't aerate to see if more of them were green when they were aerated. So, in this situation, which do you use, an ANOVA or a chi-square? Pause your video, see if you can figure that out. Okay, so in this situation, he's doing one of two things. He's either aerating or not. That's your independent variable. And the dependent variable is whether the lawn is green or brown. So you'd have to use a chi-square to compare the percentages that were green in each of the two groups. Now, since we've learned a little bit about this new statistic, the final thing that I want us to do in our class is to discern when we should use any of the statistics that we've learned so far versus when do we when do we use this chi-square statistic. And in any given research scenario, you really ought to know what kind of statistic to run. And so we're going to go through some practice exercises. But first I want to show you a framework for discerning what kind of statistic you might use in any given research scenario. So the kind of inferential statistic that we run depends on two things. The first one is the level of measurement. Now remember back to Module 1, we learned about nominal and ordinal variables. These are categorical variables. For example, gender, academic major, occupation, etc. Now, nominal variables are those that are strictly name-based categories. They cannot be ordered in any kind of way. Gender is a nominal variable because males and females can't be ranked. Academic major, occupation, these are all great examples of nominal variables. Ordinal variables are things that can be ordered or ranked from highest to lowest or worst to best, something like that. Interval ratio variables are numerical scores that fall on a number line, and they're compatible with the full range of mathematical manipulation. These are things like height and weight, number of errors, IQ scores, etc. And we know, remember, the difference between interval and ratio variables. But the point of this slide is to indicate to you that in statistics, we treat nominal and ordinal variables as if they were the same. Even though there is a slight difference of nuance here, these are both categorical variables, and the kinds of statistics that we run will be the same whether they're nominal or ordinal most of the time. Similarly, if we have interval or ratio variables, these are numerical scores. They fall on a number line, and we consider these as if they were the same. And so it doesn't really matter whether you have interval or ratio variables most of the time. Usually, you're just understanding that these can be subjected to the full range of mathematical manipulations, so you can compute an average, which is integral in computing almost every parametric statistic that exists. Now, the second principle on which we can decide what kind of statistic to run is the number of variables and the number of levels that are extant in that research situation. So the variable itself is the thing you're interested in. You probably could cite several examples yourself, but here are some examples. You might have colors of something, levels of happiness, race, quality, age, etc. Variables that are nominal or ordinal have levels. These are groups or categories. Variables that are interval and ratio don't have levels. So some examples of levels would be like the variable of color might have several levels, red, yellow, green, etc. Those are different categories or groups. The variable of gender usually has two levels, like male and female. But if you have an interval ratio variable, that's like height or weight, it doesn't have levels. You just say what the number is on the number line. So if somebody weighed 126 pounds, that would be their measurement. If somebody else weighed 152 pounds, that would be their measurement. So there aren't levels, there's just a value that's given for that variable. Now, when you're deciding which statistic to run, you have to base it on both of those things we just talked about, which are the number of variables and the levels of them, as well as the type of measurement, the level of measurement of that variable. So, I've split out in this table down below what kind of statistic you should run, that's the test, based on information about your independent variable and your dependent variable. So, if your independent variable has a level of measurement that is a single value, in other words, it doesn't actually have a level of measurement at all, and you have just one level in that independent variable because it's just a single value, then you would have to look at what's going on in your dependent variable situation. If it's interval and ratio, then you'd run one type, and if it's nominal or ordinal, then you'd run a different type. Now, what am I talking about here? Think back to when we did the single sample t-test. You remember that in that situation, you would compare one score, like somebody's IQ, against the population parameter that was known. So the average IQ in the country is 100, and you might take a sample of people and compare their average IQ against that average in the population of 100. So knowing that, we can then work backwards and kind of say that if we had an independent variable that was a single value, that means we have one group we've drawn and we've given some kind of treatment to, and we're comparing that one group and their interval ratio dependent variable of IQ against the population parameter. Now, if we had a very similar setup where we had a group of people and we were comparing that group of people on a nominal or ordinal variable, like the percentage of people who were male in that group, against the null hypothesis that it should be 50-50 males and females, then we could run a chi-square to say, for instance, if we drew this sample of engineers and determined that, 70% of them were male, and we were comparing them against the null hypothesis that it should be 50% male, then we would run a chi-square statistic to see if that were a significant difference. All right. If you had a nominal or ordinal independent variable, that is to say, if you had a categorical grouping variable, this is mostly what we've dealt with through the whole course, and there was just one of them with two levels, then of course, if you in this situation, you would also use an interval ratio dependent variable where you could compute a mean. Then you would run a t-test. Now, if you pause your video for a moment and think back to the t-test chapter, or to the module about t-tests in which we ran independent samples t-tests, then you should be able to recognize that in this situation we had groups of men versus women, nominal or ordinal, men versus women, on some characteristic, like performance on a math test. That's two levels, men and women, and some variable, performance on a math test, and we could compare, using a t-test, their performance on the test across those two groups. If you had a nominal or ordinal variable for your IV, and you had 2+ levels of your independent variable, then again, if you had the ability to compute a mean for your dependent variable, you would run a one-way ANOVA. This is, of course, only the case if you have one independent variable. If you have one independent variable and you have 2 or 3 or 4 levels of that variable, then you could run a one-way ANOVA. Some examples of this might be like if you were trying to compare, are there differences in the speeds that people drive depending on the type of car that they're driving? That might be one example. Another example might be, are there differences in the weights that people and how much people weigh based on what kind of lifestyle they live. And you might have like a sedentary lifestyle, an active lifestyle, an outdoors lifestyle, a gym rat lifestyle, or whatever. And based on those different lifestyles, remember these are the levels of the independent variable, then you could compute how much people weigh on an interval ratio scale and run a one-way ANOVA to see if there are differences across those levels. If we had a similar situation, but instead of having just one independent variable, if we had two or more independent variables, then we would run a factorial ANOVA. Remember, this is a situation where you have multiple independent variables and you're comparing, are there differences across the levels of each of these multiple independent variables. So, for instance, you could compare, does the amount of time spent studying, small, medium, or large, and does your access to a tutor, yes or no, influence the grades that you receive in a class? So the two variables here would be how long you spend studying and whether you have access to a tutor, and each of those variables has multiple levels. The first one had 3 levels, small, medium, large. The second one had 2 levels, yes or no, and you could evaluate the grades that are obtained using an interval ratio scale on your DV, and that would result in a factorial ANOVA. If instead you had an interval ratio level of measurement for your independent variable, then if you also had an interval ratio dependent variable, you would run a correlation or regression. Remember, in the situation of correlations and regressions, what you're doing is you're taking a couple of different variables and you're seeing whether on those scales, like graphed out, if a scatter plot shows a relationship between the dots so that it's upward trending or downward trending, and you might draw a line through those data using a regression equation. And in that situation, you've got both scales, both variables, your independent and dependent variable, measured on a number line. So an example of this might be, does the number of ice cream cones sold correlate with the number of murders in a given area? And interestingly enough, you would find that, yes, there is a correlation, but the reason for that is because both the numbers of murders go up and the numbers of ice cream cones go up in the summertime. And so there is actually a correlation there, but it's not because of one causing the other. All right, the final kind of statistic that we've learned about in this class is a variant, another variant of the chi-square. So you could see here, this is a goodness of fit chi-square, and down here, this is a test for independence chi-square. But the point is, if you have a nominal or ordinal independent variable, and you have one or more independent variables with 2 or more levels in each group, then as long as you've combined that with a nominal or ordinal dependent variable, just like we saw up here, if the dependent variable is nominal or ordinal, then it has to be a chi-square. Now in this situation, remember your independent variable, unlike before when we saw that it was a single value, here it's a nominal or ordinal variable. So you could say, do the percentage of males in each major differ across multiple groups of different kinds of majors? So before we had said, do the percentages of males differ from 50% within just a group of engineers, a single value, just engineers. Here we could say, do the percentages of males differ in psychology majors versus anthropology majors versus nursing majors versus engineering versus communication versus business versus math, etc. And then each of those would be a level of that variable that's a nominal or ordinal variable, a categorical variable. And because you're just saying the percentage of males, yes or no, male or female, this binomial variable, because you're just comparing the percentages here, then you would use a chi-square. Now, I don't need you to know that this is a test for independence chi-square and this is a goodness of fit chi-square. I just wanted to illustrate for you on earlier slides that there were a couple of different kinds of chi-squares, so that when I showed you this slide, you could understand that the reason why chi-square appears in a couple of different places here is because there are a couple of different kinds. Now, before I move on, I just want to tell you that I'm going to take a few slides and illustrate for you these 7 different kinds of statistical scenarios and give further examples of each one so that you can better concretize each of these situations. If you feel like you've already got a grasp of this, you can skip past this to the exercises. But just to further instantiate it, just to make sure that we've really understood these principles, I'm going to walk through each one. So category 1, this is when we have a single group of participants with just one interval or ratio score for each participant. We always, in this situation, will do a single sample t-test if the population average is known, or if you have a theoretical value in mind. So some examples might be if you measure a group of students and see if they did better than chance performance, like 25% correct, on a multiple choice test. You could also measure people's attitudes about abortion and see if they're significantly different from neutral, that's the central point, 4 on a Likert scale from 1 to 7. 4 is the middle, and you could say, are they different from neutral? Are they either positive or negative? Category 2, as we said before, is a single group of participants with one nominal or ordinal score for each participant. So in this situation, we have to use a chi-square if there's a reason to specify a null hypothesis about how much should be in each category. In such a case, we might do something like this. In past years, 35% of the US population got a flu shot. A researcher could compare the percent who got a flu shot this year, like 20%, to previous years and see if this year is different. In this case, what's the DV? It's a nominal dichotomous variable or binomial variable. It's yes or no. That's it. And so because there's just 2 options here, then we have to say, what is the percentage of people who did get a flu shot in this year versus other previous years? Category 3 is when participants are defined by a single independent variable with 2 levels, and they have as their dependent variable an interval or ratio score. In this case, we would do either of 2 types of t-tests. We would do an independent samples t-test or a paired samples t-test. Remember, independent samples are used when we have a between subjects design with 2 different groups of people, and we're comparing between the subjects across the groups to see if there are differences. An example of this might be, you want to see if green light can reduce the pain associated with a migraine, so you expose one group of patients to a green light and another to a white light of the same brightness, and you see, you measure their level of pain after you've exposed them to those things, and that's the dependent variable, the level of pain. A paired samples t-test is used for within subjects designs, as you recall, when you take the same people and you measure them more than once, like pre-post. So in this case, you might have if you use the same research question about the green lights, but you expose the same people to both types of light, and of course you would want to do this in a counterbalance design so that you started some people on the green light and you started other people on the white light, and then you switched both groups to view the other kind of light. But everybody has done both, and you measure the difference between their pain in the first kind versus the second kind to see if their pain was better or worse depending on which type of light they were viewing. Alright, category 4. This is when you have 3 or more groups of participants that are defined by one independent variable. I said on the other slide that it could be 2 or more groups, and that's, I don't know if you remember this, but in a previous module I told you that when you're doing a one-way ANOVA, that it's the same as a t-test if you use 2 groups. But the only difference is that an F statistic that you've computed for an ANOVA is equal to the T statistic that you've computed squared, because the ANOVA is still in the variance form, it's still in this squared form, and the t is not still in that form. It's been analyzed based on the mean differences, so those have already had their square root taken, and they've been shrunk back down to that original unit. So you could say, on the one hand, that it needs 3 or more groups in order to use a one-way ANOVA, because if you had 2 or more groups, then you just do a t-test. But really, you could technically do an ANOVA with 2 groups. It's just that the results from an ANOVA and the results from a t-test will always be the same. So usually people will say, if you're doing an ANOVA, that you need at least 3 groups. Of course, your dependent variable needs to be interval ratio so that you can compute averages. And an example of a one-way ANOVA might be, which of 4 different homeless signs results in the most donations? You could have a group of Confederates go out, each with one of 4 different signs. So some of them might say like something goofy, and some of them might say like a plea for help, and some of them might humanize the person, and some of them might be just really, really goofy. But in a situation like this, you could count up the money, the average amount of money donated to the person who's holding each of these 4 different signs. And that would allow you to measure on an interval or ratio scale, your dependent variable, money, across different numbers of groups. So here we have 4 different groups, and that's your independent variable. A repeated measures one-way ANOVA could be used for within subjects designs. So if you recruited a single group of homeless people and you had them rotate through the 4 signs so that each person held one sign, then the next sign, then the third sign, then the fourth sign, and that would allow you then to compare across the same person the effect only of different signs. And basically everything else about the study would be the same, but it would just be considered repeated measures in that situation, because it would be the same people with multiple conditions. Category 5 statistics are those that are groups of participants defined by more than one independent variable, and each one still has this number line kind of dependent variable where you can compute the mean. This is, in order to do this, we would use a factorial ANOVA. An example of that might be a data analyst at a major bank wants to know whether the level of debt is related to their income bracket, low, medium, and high, and also whether it's related to their job type, white versus blue collar, or both, or some interaction between the two. And so here this would be a 3 by 2 factorial ANOVA, and our dependent variable is level of debt, probably measured in dollars. We could also do a repeated measures factorial ANOVA if we only have IVs that are within subjects, if all of our independent variables are repeated. Or if you have some that are repeated and some that are between, then you use what's called a mixed ANOVA. And that would be where at least one of the variables is between subjects and at least one of the variables is within subjects, meaning across different people, repeating the same people. In these cases here, and in the case also of one-way ANOVAs, you would do post hoc tests like Tukey's HSD to determine where the significant differences lie between the groups. Your category 6 statistics are when you have a single group of participants, but you've measured each person on 2 number line scales. Here you do a Pearson correlation or a linear regression or both. A Pearson correlation, an example of that is there a relationship between the years of education that you have and your annual income? You might measure a single group of people on both of those variables and then plot them against each other and use an R, a Pearson correlation statistic is R, to see what is the strength of the relationship between those 2 variables. A linear regression allows us to predict the income someone might make based on their years of education. So it's the same situation as up here, but after we make that scatter plot, we might draw a line through it that has a particular prediction equation for guessing how much somebody would make based on how many years of experience they have. And the way to decide between these statistics is to see if the research question asks about a relationship between the two variables, that would be a correlation, or if it's asking about predicting one based on the other, and that would be regression. So like I said before, a Pearson correlation would yield a coefficient like r equals 0.7, reflecting a pretty strong relationship between two variables, and a regression would yield a prediction equation, something like y hat equals 3x plus 4, where y hat is the predicted value of your dependent variable and x is the values of your independent variable. Finally, category 7 is when you have two nominal or ordinal variables and you're pitting them against each other. So an example of this, in this situation, you would always use a chi-square, and an example of that could be you take a radar gun and sit on the side of the highway clocking cars. You're interested in whether the kind of car you drive influences whether you speed. Your first independent variable is the color of the car being driven, as you can see up here. And in this situation, we might only look at black, white, yellow, and red cars. And your second is the style of the car, whether it's a sedan, a coupe, or a hatchback. And you would define speeding as anything 5 or more miles per hour over the speed limit. And then you could code each car as either yes, they were speeding, or no, they weren't. And if you look here, yellow and red coupes are much more likely to speed than other kinds of cars in this table. Everybody else is much lower than this 80 and 75% of speeding cars. A goodness of fit chi-square is used to evaluate the observed proportions against hypothesized distributions, whereas a test for independence is used to see if there's a relationship between the two nominal variables. This right here is a test for independence because you're seeing, is there a relationship between the color of the car and the type of car being driven in whether somebody speeds or not.